On January 17, 1991, at 2:30 a.m., the opening attack of Operation Desert Storm was set in motion. Tasked with crippling Iraq's command and control, shipborne Tomahawk and B-52 launch AGM-86 cruise missiles were employed to infiltrate targets within Baghdad. Alongside this initial inrush of deep-striking assets was a new class of weapon. This attack was the first public debut of a stealth aircraft facing off against one of the largest air defense networks in the region. The iconic Lockheed F-117 Nighthawk, the first stealth strike platform, were among the first sorties to enter the heavily defended airspace of Baghdad. Supported by standoff electronic jamming F-117 aircraft and possessing no radar, guns, missiles, or defensive countermeasures, it relied entirely upon its ability to remain hidden from radar, to penetrate Baghdad, drop its two laser-guided 2,000-pound bombs, and egress with impunity. The success of these initial strikes, coupled with the punching of a hole in Iraq's early warning air defenses by Apache attack helicopters, paved the way for a massive bombing effort over the next 24 hours, composed of over 2,600 sorties targeting command and control bunkers, missile launch pads, equipment storage areas, communication facilities, and airfields. That night, the need for stealth was proven, cementing itself into the list of must-have capabilities of any new aircraft program. But where did this peculiar classified aircraft emerge from, and what technologies made it so stealthy? It all started in the 1960s with a Soviet physicist and his undervalued equations. In order to understand how stealth technology emerged, we need to quantify what stealth is. Stealth isn't one specific technology, but rather a mantra of design that incorporates low observability. The ability to detect an aircraft can range from simple visual and acoustical detection to more sophisticated means such as emitted radiation detection and tracking by infrared and radar. Of all the potential threats faced by combat aircraft, detection and tracking by radar pose the most risk. Radar, infrared, and optical detection all rely on the bouncing of electromagnetic radiation off an object in order to gather information from it. However, radar differs in that the source of the reflected radiation is actively emitted from the observer. With passive methods of detection, the target's own emissions or ambient light are used. Radar relies on beaming radiation out into a volume of space and analyzing the resulting reflected energy to detect and track. Aside from the source of the radiation, the wavelength of the radiation differs between detection methods. Visible light has a wavelength range of 380 nanometers for violet light down to 700 nanometers for red light. Infrared light occupies the wavelength range below that, between 700 nanometers and 1 millimeter. Below this is the realm of radar, the region of the spectrum known as microwaves and then radio, ranging from 1 millimeter all the way to 3 meters. While detecting an aircraft provides a warning, in order to defend against it, it must be tracked. Tracking is the determining of a target's position, velocity, and heading from a reflected signal. A tracked aircraft is in effect targetable by missiles and anti-aircraft artillery. Smaller wavelengths allow for more resolvable detail, making tracking easier, but this is compromised by range. As a general rule, the smaller the wavelength, the higher the atmospheric absorption and attenuation of the wave. While some air defense weapons can track optically, infrared tracking is the predominant method for close-range air defense due to its ability to see the heat of an aircraft through the atmosphere. Infrared tracking works by using an infrared sensor similar to a camera to look for the highly contrasting signature of hot jet exhaust gases and the warm aircraft body against the ambient air temperature. Because of atmospheric absorption, infrared radiation can only be used for tracking at short distances, typically 20 miles or less. Infrared homing weapons are usually found on short-range anti-air missiles mounted to vehicles or in shoulder launch systems called man-pads or man-portable air defense systems. The Stinger missile is a commonly used example of this. In contrast, the longer wavelengths of radar detection and tracking are what makes it so powerful, its ability to penetrate the atmosphere at much further ranges. The first military use of radar began around the start of World War II. One of the more notable uses was in the air defense of England. By 1939, a chain of radar stations protected the east and south coast, providing early warning to incoming aircraft. This early radar operated on the longer wavelengths of radio and offered very coarse information on incoming contacts. That same year, a breakthrough in research resulted in the invention of the resonant cavity magnetron. This allowed for the generation of shorter wavelength microwave radiation at large amounts of power. More detail can now be assessed about the target, such as its heading, altitude, and velocity. Practical tracking radar was now possible. Fast forward to today, and most military airborne radars, including those found in radar-based anti-air missiles, operate in the 5 cm to 1 cm wavelength microwave range, as it provides a good compromise between range, resolution, and antenna sizing. At these wavelengths, tracks at distances of about 50 to 80 miles are possible. It should be noted that wavelengths from 5 cm to 30 cm are also used on ground-based early warning radars that can track targets up to 250 miles away. With a proper radar track, a firing solution can be determined, with only evasion, electronic jamming, and the dispensing of radar clouding countermeasures known as chaff offering any form of defense. Because missiles are effectively guided rockets, they have limited amounts of energy available to them to maneuver. If the target can deplete this energy before it is within detonation range or obstruct the missile's ability to maintain a radar track, the missile can be defeated. This is known as going defensive in air combat. The goal of radar stealth is to both mask an aircraft from being detected